All right, let's begin. Simple machines. So, the idea of simple tells you that we are going to be talking about basic machines that we do not need battery or electricity or anything to drive. It's just our hand, mechanical. They're mechanically operated. That's all. That's all. That's the way we describe them. Simple machines are mechanically what? Operated. So, and what's the machine? Is any device rather that makes work easier and faster. Exactly. Now that idea is very important because if it doesn't make your work easier and faster, then it should not be called a machine. Why did I say that? If you want to lift something, for example, no, for example, if I want to move this thing, if I want to move this thing from one place to another, I could incline this thing at an angle and put this guy here, and by itself, it will move, right? So, if the effort that I put into it, it must be less than the load. Because if that is not the case, then it means that I am at a disadvantage. Do you understand now? All right. So there are various terms we use in describing machines. First, our simple machines that we're going to be looking at are the levers. We have the levers, the gears, the inclined plane, like I just mentioned, inclined planes, wheel and axle, the question we saw, wheel and axle, pulleys, pulleys, wedges. I'll show you what they are. We also have this guy, um, screw jacks, screws and screw jacks, screwdriver, screws. Yeah. So, but these are the ones that you will see in your exams. This seven or six, 1, 2, 3, 4, 5, 6, 7. Those are the ones you will see, and those are the ones we are going to be talking about. Exactly. All right. So the first terminology that we use to talk about our machine is mechanical advantage. No, not mechanical advantage. Let's have the basic one, effort. 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 This is the force. This is the force. This is the force input. Let's put input. This is the force input. Alright. So I wanted to say that it's the force that we use to overcome rather the load, and that is correct. So simply say force input, you already understand. The force that the person, individual, imputed into the system to overcome the load. Then, what is now the load? The load is the force output. Here is a force input, and the load is the what? Force output. So that is the force that is to be overcome. Exactly. The load is the force that is to be overcome. Now, um, then there is the mechanical advantage. Mechanical advantage. Short MA rather. Now, MA is called the force ratio. It's also called what? Force ratio. Because your MA is your force multiplier. What do you mean by force multiplier? I want to carry a load of 500 Newton, and I only imputed 50 Newton. By using 50 Newton, I'm able to carry what? A 500 Newton load. Do you see that you multiplied my force by a factor of what? 10. Do you understand now? Alright. So I now get the 10. Basically, the load over effort. Does it make sense? Alright. So the formula for MA therefore is what? Load over effort. Load over effort. Is it clear? All right. Now the third term. Another thing is we can also say since load is force output, so we can also say is what force output over force input. Alright, so this one describes the fact that it is force ratio. Alright, let's go to the next one, which is the velocity ratio, the VR, VR for short. Now the VR is the one that this one is the one that has many formulas. Okay, so but the simple formula is actually you see velocity ratio. You know this one mechanical advantage has to do with you and the load, the force you're imputing on the load. But velocity ratio is about the machine itself. It's about what? So it depends on the geometry of the body of the machine. So for example, some things are more efficient than the other. For example, you cannot compare, look at an inclined plane system, for example. You cannot compare the amount of work it will do to that of a pulley. You know, you people know this thing now, those of us that are lapos. You remember this pulley that you use to draw water from the well? It will be over your well like this. So you now be rotating this drive, right? This is a pulley. Do you understand? Can you compare the work it will do to the work that an inclined plane will do, for example? You know that if you want to pull, for example, a very huge box out of the well, is harder than if you want to push it from somewhere here on an inclined plane. Do you understand? All you need to do is put the inclined plane on a good edge and the guy will slide down. Do you understand now? So the velocity ratio is dependent on the geometry of the machine, the orientation of the machine itself. Alright. So that's why the formula of the velocity ratio will change depending on the machine. Now the velocity ratio, but generally is actually the effort over load. Actually, we say it is the distance moved by effort over distance moved by load. Now, this formula actually comes from the lever. Look at this lever, for example. I pivot this point and I want to overcome this load. Okay? So if I want to overcome this load, let's say I want to lift this thing, I will apply a force downward, right? So you will notice that if I want to move this thing from this point to this point, let's call this displacement x of my effort, x of e. This guy will move, if I move this thing down, you know that the line will come in this direction. Do you see the distance that the load moved? X of load. So it means that this machine is very efficient. Do you understand? So that I'm just trying to make you see where the formula is coming from or the use of the formula. It relates the distance moved by the effort to the distance moved by the load. Alright. So let's now talk about the different formulas for velocity ratio. So begin with the lever. With the lever, is this way. Exactly. But with the gear, it's different because gears are different, right? You know, a gear is, you know, this is your, yeah, bicycle. Thank you. I wanted to even use this machine grinder. But bicycle is a good one too. You notice there's this and machine and bikes. What's the name? Bike. And what's the English? Is it bike? Motorcycle. Thank you. So. Let's go. So you know there is. Don't worry. So you know there. Listen, please. There will be a gear here. that will be driving another gear. In other machines, those gears are conjoined. I want to use a conjoined one. But a gear is basically a round object like this that is now toothed. Is toothed, 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 toothed. Now, it will be driving a bigger gear that is also toothed, you know. No, for the ones that are not conjoined. Do you understand? So this one they are conjoined. So this one is the driving, right? And this one is the what? Driven. This one is the driving because it's this one that is controlling this one. Now let me ask you, because you notice that the diameters are different, right? Or the radius is different, I know what you are given. Which one will move more than the other? Is it this one or this one? Which one will undergo more cycles? The driving? Yes, because it's smaller. Do you understand? This one will be taking, as this one is moving, this one will have completed a circle before this one completes the circle. Is it clear? So using the formula we talked about is the effort over the load. So it will be what? Driving over driven. So if we are discussing, if is diameter you are giving, you say diameter of the driving over the diameter of the driven gear. If it's radius, it will be radius of the driving over. If it's cycles you are giving, number of cycles, number. Is it correct? Alright. Alright. So that's for gears. Now what about inclined plane? So the velocity ratio for inclined planes, the velocity ratio for inclined plane is simple. It's simply 1 over sine theta. How does an inclined plane look? This is our, we want to carry, see, this is what I mean by inclined plane. I want to, this is a, for example, this is a bus, what do you call this, a lorry. So I want to get a load out of the lorry. So I put a plank on the ground. Does it make sense? So this is an inclined plane. This is my lorry. It's not a lorry. Do you not understand? Does it not look like it? Okay, here's the point. So this guy, I want to bring out this guy from the lorry. So and I incline it. You have to carry. No, I basically roll it and it comes down. Do you understand? So this angle theta is the angle to the horizontal, never to the vertical. Theta is what? To the horizontal. Alright. Then the next one is wheel and axle. Wheel and axle. Okay? For wheel and axle is simple. It's just a machine that looks like this. There is going to be a wheel driven by the axle. Is that correct? So the axle is, okay, this is what you remember it. What does axis mean? Center. Do you understand? Center. I was going through this thing. Do you remember the bone of the vertebra that allows for nodding? For nodding, it is atlas. For rotating, for saying no, is axis. Don't forget to. Once you remember this rotation, that's axis. Is that clear? Right, so axle, this is the axle, and this is the wheel. So the velocity ratio will what? Since it is the wheel that will be driven by the axle, then to be wheel over axle. So whatever is given of wheel, maybe the radius of the wheel, exactly, radius of wheel over radius of axle. Just any information given about each of them, it will be that of wheel over axle. Alright. Then What's the next one? Pulleys. Now with pulleys, there are different types of pulleys also. There are different types of pulleys. And also, see, this one, it can also be number of teeth of driving over number of teeth of driving. Just all you do is count the teeth. How many teeth does it have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Just now. So the number of teeth of driving over number of teeth of driving. Okay, so for the pulleys now, there are different types of pulleys. The first type of pulley is the very basic one. So here, there's a here's a pulley. This is what a pulley is. There's a rigid structure connecting something. So you want to lift this load. You're applying your effort here, and your load is here. Is it clear? So you are drawing. Do you understand now? Alright, so that's a pulley. Now, there are different types of pulley system. This is a simple pulley system. In this simple pulley system, how many pulleys do you have? One. So your velocity ratio will be 1. Is it clear? It's the number of pulleys that determine exactly. So if I have, for example, I have, how do they connect it? There's a way they will connect it like that. No, there is space. So such that this one will link to the other, will link something like this. Then the load will be on the last one. So this one, what will be the velocity ratio? 3. Is it clear? 3. But if the pulley is like this, a system where there is a pulley at the top here, then it's connected to another pulley, and this one is connected to another pulley. Do you see the system? Where the pulley is like this. The formula for the velocity ratio will be 2 raised to power the number of pulleys minus 1. Raised to power the number of pulley minus 1. Is it clear? This one has come out once before. Okay, but this one is the most common one. Is that clear? Just count the number of pulleys, and that's the velocity ratio. But for this one, 2 raised to power number of pulleys minus 1. Alright. So that's for pulleys. Then what about the velocity ratio for wedges? Now what's a wedge? What's this? What does it look like? Ah. This guy. Axe. It's an axe. So this point of the axe is called a. Doesn't look like axe. No, the ones you know are the ones that have this thing extension at the back. As woody. The metal one. The mount.
Looks like they put a big plane around.
Okay. The point is I want you to see this. So this is the shape of the wedge. Is that clear? We use it to tear into woods, for example, right? It will enter the wood like this, isn't it? When you hit it. So it's used to overcome this load. Now, the velocity ratio for wedges, the VR, will be the slant height, the length of slant height over the thickness. The length of the slant height over the thickness. Is it clear? Alright. Then the next one. Screw jacks, okay? Now how do screw jacks look? You know jack now? I don't know the jack you know, but there are two that I know of. There's one that looks like this. You know it.
With cars.
So there's something you'll be turning here that bring this guy up. And there's this very common one. This one is very common. And you're using yes. So that thing you put it there, and the guy will be moving up.
Yes. Now that this is to peel apples. Yes, no.
Jack,
Like that.
skill Jack for lifting cars. Let's have this my diagram that put out. Okay. But me, I've not seen it before. It doesn't feel nice, man. It is nice. So I don't know, but really. Let's go. So the velocity ratio will be equal to now turning this thing will take a number of circles, right? So that circle will be 2 pi r because circumference of that circle. Then divided by once this guy goes in one circle, the what's it called now? This thing will move up a little. Move up a little. The same way here. As you turn this guy, you have to move up a little, up a little. So that moving up is called a pitch. It's called what? So it will be 2 pi times the radius of the guy over the pitch. Is it clear? You'll be given the pitch, you'll be given the radius of the screw jack. You just know how to use it.
And the guy will use
And you know what pi now 20%. Alright. Alright, so let's go to efficiency of machine now. Efficiency of machine.
I think inside let's say that we use to find the header or the circle that we use to find.
No, mathematically 2 pi is 360.
For this one, I will not do by R over the pitch. I'm 316 as the radius.
No. No, for other forms of you have to calculate in length. Pi will be like 22/7. Because radius will be given in length. So you don't use degree to understand. So you use the value, I don't know what they call it. You don't use the radian value of pi. The radian value of pi is 180 degrees. Do you understand? You use this one. You use 22/7. Alright. I mean, of course, when you see your question, you know which one to use. There's some questions that will leave pi. They will not turn into anything. So it will still contain pi. Alright, so what is efficiency? Now the efficiency is basically wait. Anytime you have efficiency, because we also do it in electricity, efficiency is always your output over your input. We call it work output over work input times 100. Now it is denoted by this sign. Exactly. Efficiency. Now, you see, what is work? What's the formula for work done? Force times distance. Good. So it will be force times distance r, for example, or let's just put force times distance. Now, since it's output, it will be distance moved by what?
Distance moved by
This force. Let's first write the formula. Okay, it's the same. Here it will be force times distance. Now, but are you with me? But output is Force times distance moved
by the law.
by the load. God bless you. Do you understand now? Because your output is the load. Makes sense? Then this one will be force times distance moved by the effort. Is it clear now? Now, what is the force that we are imputing?
Is therefore
The force that we are that is going out rather. The force that's going out. What's that called? We call it load. But the force going out. Does it make sense? The force going out because it's output. We are talking about output. So distance will be distance moved by load. Then the force will be what? The load. So the value of the load times the distance moved by load. Let's put this over here or DL over what's this force now? Input force. What do we call input force? Effort. Effort times distance moved by effort. Is it clear? Now times 100 over 1, like we said. Now, if you look at this very well, what is this?
that one is already
Load over effort, which is what?
MA.
MA, load over effort.
That one is effort overload.
Is it clear? So, MA times DL over distance moved by effort. You remember that velocity ratio is distance moved by effort over distance moved by load. So it's as if we inverted it, right? So it means that this thing is actually 1 over VR. Do you understand? So MA times 1 over VR times 100. So N therefore becomes MA over VR times 100. Is it clear? So this is the final formula. Now let's solve questions. Do you still have those questions? Some people were not in class yesterday, so let's bring them now. Thank you. Were you with us yesterday when we did it? The question on machines in the online class. Okay. Okay. Should I write on the board? Let me write the question on the board. Let me pause this. A machine whose efficiency I'm coming. A machine whose efficiency is 75% is used. So we already have the efficiency 75%. So now listen, there are two ways of going about solving this. Let me go on first. Is used to lift a load. The load is 1000 Newton. Calculate the effort put into the machine. If it has, so we have to look for E. If the velocity ratio is 4. Remember that, or recall that N, or it has a name, I've forgotten the name, is a Greek letter. I've forgotten. So that this efficiency is equal to MA over VR, right? And mechanical advantage is what? Load over effort. Okay, so from here we can find M, since M is what we're looking for, is equal to what's the load? 1000 over, thank you, over effort. Is this clear? So we use this to represent this in our equation, times 100 over 1. Now this becomes 1000 over E divided by VR, which is 4. Now listen, this times 100 is not necessary here again, since you are giving 75%. You can just come here and say it is 75 over 100. I mean, if you don't understand, it's the same as if you pick 75 here and put times 100 here. It's the same. Alright. So we'll bring our 100 here. So from here, we can cross multiply 100 times 1000 over E, right? This thing will multiply this guy, and this one multiply this guy is equal to 75 times 4, 150, 300. 300 is equal to this by this, 100,000 over E, right? So E will be equal to 10,000 over, no, 100,000 over 300. So what did he say again? What did you? Yeah, yes, 0.3. What's the unit? Newton, because it's a force. Alright. For the second one, a wheel and axle is, Esther, do you understand? Okay. A wheel and axle, oh, okay. No, don't worry, because you're following, you understand. A wheel and axle is used to raise a load whose weight is this. So the load is what? 80 Newton. When an effort of 250, E is 250 Newton, is applied. If the radii of the wheel and axle, so radius of wheel is what? 800 millimeters. Radius of axle 200 millimeters. So what would be the velocity ratio? Radius of wheel, which is 800, over radius of axle. What does it give us? 4. So VR equals 4. Alright. So from here, we need mechanical advantage also, which is what? Load over effort. And that's what? 800 over 250. So 5 here, 5 here, 16. Now be 16 over 5, which is 3.2. Exactly. So from here, therefore, efficiency is equal to MA over VR times 100. What is MA? 3.2 over 4 times 100. Here 125. 25 times this. 25 times this. 80. E equal to 80%. Is it clear? Do you understand what it is? Where? Here? You know, velocity ratio is for wheel and axle is wheel over axle. They told you wheel and axle are this. This one will be for wheel and axle respectively. That is this one for wheel, this one for axle. So we got 4. The mechanical advantage is load over effort. So we calculated that we got 3.2. Then efficiency will now be mechanical advantage over velocity ratio times 100. And it's mechanical advantage, not advantage. Alright. Teach. You just did sound right. Heard you did. Stress pattern, were you giving rules? Words ending with this, words ending with that. Ah. Alright. We'll continue into elasticity. Okay? Elasticity. One more question. Okay, give me one. There's something you should take note of here. Ideal machine. There's no ideal machine. An ideal machine is a machine that is 100% efficient. So how does a machine become 100% efficient? If ratio of MA to VR is what? 1. And when can that be so? It is when MA is exactly equal to what? VR. So VR there, wheel over axle, that was bigger over small. Is it clear? Is it a hard question? Good. Do you understand this, sir? You don't understand? You weren't listening. It says, in an ideal wheel and axle system, R stands for the radius of the wheel, and R, small r, is the radius of the axle. Big R, radius of wheel. Small r, radius of axle. It now says ideal wheel and axle. If it's ideal, efficiency will be 100%. And we said that does not exist. Okay, but it's trying to tell you this thing. So it can only happen when MA is equal to VR. So VR, do you say it exists?
No, I don't. But
Why can we not have an ideal machine? Friction. Do you understand now? In fact, that's the reason why your velocity ratio is the way it is. Because some, now listen, in your effort, if you are told to calculate your effort, your effort for some, that's for some questions where they'll say calculate effort, and they'll just give you the uh, the um, no, how did they ask that question? There's a way they ask that question that you simply add the work done to overcome friction plus, okay, hey, work output. Exactly now. They ask you to calculate the work output. It has to be the work done to overcome friction. No, the work input. Do you understand now? It will be the work done to overcome friction first, plus the work output. Exactly. Because the work output, I mean, the work input will have to first overcome friction. So some of the work is already wasted. I don't know if you understand. That's why it cannot be 100%. It's already wasted on friction, then the output. Is it clear? All right. I guess we are good. Do you have one question as usual? Okay. All right. Let's go to um, elasticity. Right. Elasticity. All right. Now, um, elasticity is one of the properties, right? Elasticity is one of the properties of solids. Elasticity is one of the what? Properties of solids. Of the properties of solids. The other properties include for metals. Now, this one is specifically for metals. We have malleability, ductility, then the ones that are for non-metals. We now have brittleness. You know, they ask this question 1 year about brittleness. So I want to explain the difference, the meanings. All these are all properties of solids. Elasticity, malleability, ductility, and brittleness. What's the difference between them? Malleability is the property of a metal to be beaten into sheets. Sheet. Do you know what sheet is? Yeah, a thin, spread out, that has an aerial this thing, like your roofing sheet. Exactly. So that is because the metal is malleable. The metal is what? Then ductility is, you say something is ductile. It means you can stretch it into tiny wires. Do you understand now? You can. That's why we're able to make our cables from metals. So that's ductility. Don't forget it all. Malleability, beating. The way I remember it is malleability looks like hammer, like you are hammering something. So you beat it to tiny sheet. Ductile, like something like, it sounds like stretching, right? Then brittleness is breakability. Yes, if something is breakable. So for example, which guys will have this property? That can break. Things that can break. Ceramics. Non-metal, it doesn't mean gas. Whenever I mention, no, this is not chemistry now. Whenever I mention non-metal, the first thing that comes to mind is gas. Ceramics, they are also solids. But when I say solids, you should come to your mind now. That is not gas. So, brittleness, ceramics can break. What other things can break? Glass, is that clear? Alright. So that's brittleness, ability to shatter upon hard impact. But today we are dealing with elasticity. Elasticity is defined as the ability of a body to return to its original state, the ability of a solid substance or a substance to return to its original state after it has been deformed, to return to its original state after it has been deformed by a force. By a force. Who has rubber band here? God bless you. God bless you. Happy birthday. Deformed by a force. It has undergone deformation under a force. Now, an elastic material is able to return to its position when you deform it. Exactly. So look at the original state of this thing. The original length of this is like this. Now if I apply force on it, and I release the force, see it returned to its original state. Is that clear? But there is something with elastic materials. There is something with them. There are sometimes that when you deform them, over a very huge force, under a very huge force rather, they are not going to be able to return to their position again. Alright, so that was what Hooke studied. Now right, Hooke's law. Hooke's law. This states that the force applied on an elastic material, is directly proportional. The force applied on an elastic material, is directly proportional. An elastic material is directly proportional to the extension produced. The force applied on an elastic material is directly proportional to the extension produced. Directly proportional to the extension produced, provided that the elastic limit of the material is not exceeded. Limit of the material is not exceeded. So every material has its own elastic limit. Every elastic material. For example, I stretch it to this point and it's able to return. If I stretch this thing to a length as much as this, there are two things that could happen. It could break. Do you understand? We call it breakage. Do you understand? You say cut because it's tiny, but it could be even elastic metals, when they make a spring, do you understand? So that one too could break. So when it shatters, they will say it has undergone breakage. Exactly. So let's quickly mathematically express Hooke's law. They will see the graph. You see, Hooke's law says that the force you apply will be directly proportional to the extension that is produced. What that means is that if I apply small force, extension is small. Larger force, you will notice that in fact it's pulling back my hand, right? So small force, small extension. Larger force, larger extension. Even larger force, larger extension. Do you understand now? Alright, so the point is that the extension will be proportional to the force. Okay, so with this we introduce our constant. F becomes what? Ke. Exactly. So that means that for any set of materials that has the same constant, then the ratio of the force to the extension will be constant. Divide both sides by E. Exactly. that the constant will be equal to what? Ke. Is that clear? So for a set of materials under the same condition, the F1 over E1 will be equal to what? F2 over E2 will be equal to what? F3 over E up to any number of F's. Is that clear? Another way to present this is F1 E2. Now that will confuse you, so let's not use it. But of course, it's the same as F1 over F2 is equal to E1 over E2 because F is direct proportional to E. Is it clear? Alright, so put this down. Now, let's now um, plot a graph of his law. I'm going to plot a graph of force against the extension. Okay? Take note of this graph. Now, then Ursula is saying that if we apply a force, that guy, the body has the body is going to start from a particular length. Okay? So there should be extension here against force. Do you know what I'm trying to do? So the guy has a particular extension that is, length, distance. This thing has length, right? It's going to now apply force. Alright. But usually they use F over E. I'm just trying to do the real life situation here, where there is the extension. So the body has its own length. So this is the original length. Now, and it's starting here because there is no force impacted yet, right? Then will be to begin to produce some extension that is directly proportional to the force that is applied. But a point is reached, don't try it, listen to this explanation. A point is reached beyond which, remember this, the law says that provided that the elastic limit is not exceeded. Meaning that if you exceed the elastic limit, what will happen if you exceed the elastic limit? Hooke's law will not be obeyed again. Remember, Hooke's law is that the extension is proportional to the force. So the opposite of that is what? The extension will not be. A lot of times, what students think is that Hooke's law, the opposite should be that the thing will break once it has gone beyond the elastic limit. Not yet. The only thing that will happen is that the extension will no longer be regular. It could be something like this. Do you understand now? Or something like this. It will not just be regular. Do we understand? Alright. Now, but again, there is another point beyond which if you now stretch, see, at this point here, the extension is not regular. This point here is called what? Elastic limit. But there's a point here beyond which, see, at this point, if you stretch and release, it will still come back to its original position. Is it making sense? But beyond this point, this point is called your yield point. It's called your what? It is the point beyond which, if you stretch, the guy will not return to his original. If I use this rubber band, to hold a pack of books together, a pile of books rather, together for a long time, by the time I take it after like 3 weeks, what will happen? So it has expanded. Just now. So that is because it has gone over the yield point. Don't forget, this point is what? Elastic limit. This point is what? Yield point. Then again, if you now keep extending to a point beyond the yield point, so far away beyond the yield point, it will get to a point where it will not be able to do anything again than to break. It will say it's the Coco kill me point. Do you understand? So it's called the breaking point. So at this point, your stuff will shatter. Is that clear? Don't forget the levels of elastic limit first. After the elastic limit, the guy can still return, only that the extension that it will be producing now will no longer be direct proportional to the force. Is that clear? Alright. So put that graph down. Then we will now go to Energy stored on an elastic material. Elastic spring. Elastic string. Because spring is elastic, so elastic string. Alright. So watch this. The energy stored E is given by the formula half K squared. Where K, remember this K they are the same, is the spring constant. So it's elastic spring or string constant. You know, if it's a string, the string can be elastic or inelastic. But if it's a spring is always elastic. Is that clear? So we call it force constant or spring constant. Force constant or spring constant.
I think spring or spring.
Spring constant. I use string here. You know we use the word elastic. So it will be string. But if I say spring, is elastic. Do you understand now? Elastic string will work like a spring. Make sense? We have the same kind of property as far as elasticity is concerned. Exactly. So now um, we can generate an equation here. Recall that K is F over E, right? So E therefore can become 1 over 2 dot K, which is F over E, times E squared. This takes care of 1. So E equal to what? So Fe over 2 or 1 over 2 Fe. Is it clear? Alright, put that down. Then let's talk about some properties. Are you lost, right, Matt? Okay, you are getting it. Okay. Let's talk about some properties of those elastic materials now. Mathematical properties now. So the unit. Okay, let's talk about the unit, please. Sorry, I didn't mention that. The unit of the spring constant will be Newton per meter. Is it clear? Because force is Newton, extension is meter. That's the unit of this guy. Then the unit of energy is what? Joules. Joules. Unit of energy is joules. And then, so let's first talk about the tensile stress. Tensile stress or compressive stress. Tensile stress or compressive stress. So the tensile stress is given by force is the pressure, right? Is the pressure on an elastic material. Is the pressure on an elastic material. It is given by what formula for pressure? Force over area. Is it clear? Alright. So this is tensile stress. Now let's talk about tensile strain. Strain. Now strain is not compressive. It's only tensile because it has to do with strings only. This is the ratio of the extension produced over to the length. This is the ratio of the extension produced to the length of the material. The length of the spring or elastic string. This is the ratio of the extension produced to the length of the string. Now, E is extension, S is what? Original length. Now, what will be the unit? What will be the unit of this one? Newton per meter squared. Is it clear? But for this one, what will be the unit? Doesn't have a unit. Is that clear? So which of these is a dimensionless quantity? A. Mechanical advantage. B. Tensile stress. What's the answer?
No answer.
There's an answer. Mechanical advantage.
Why?
Effort, Newton. Load, Newton. Is it clear? Don't forget though, mechanical advantage does not have unit. Velocity ratio does not have which one again? Tensile strain also, now we are looking at it, does not have unit. Is that clear? They are dimensionless. Yes. Alright. Now there's something called the Young's modulus. The Young's modulus. This is the ratio of the tensile stress to tensile strain. This is the ratio of the stress to strain. Ratio of the stress to the strain on the material. Stress of the stress to strain on the material. Stress to strain. Is the unit like gamma? I look at it. Gamma will be the ratio of what? Stress to strain. Make sense? Gamma. Gamma. Something like this. I suppose write like this. I write mine like this. What is stress? Force over area. Right? Divided by extent. What's strain? Acceleration over length. So it becomes F over A divided by E over L, which is equal to F over A times L over E. The answer becomes, the formula becomes FL over AE. That's formula for Young's modulus. FL over AE. Alright, let's pick some questions. That's all. Have we done fluid mechanics? Density. I'll send you a video on it. Okay. When I send you the video, you see the questions we solved. It's simple, but there are some that some stubborn parts. Of course. And it's as simple as just math of word. Alright, let's take these questions. Let me write some questions down. Alright. Is that a string of length 4 meter is extended by 0 point that. So a string, what's the original length of the string? 4 meters. What's the extension produced? 0.2 meter. When a load, so now let's call this small l, then the load, we could call it force, let's call it force. F is what? 0.4 times 10. No, it's load. Load is force now. Load is a force. Is it clear? This one. This is the mass So for force, mass and acceleration due to gravity. Is it correct?
Yeah.
The weight of an object is the mass of that object times acceleration due to gravity. So if you are given load here, you can easily convert. Although there are some questions that you don't need to convert, but the reason why I converted is because it gave us another force here.
Yeah.
Is it clear? So the force here is going to be what?
For
4 Newton. What will be the length of the string when the applied force? So this is F1, F2 is 15. So it says you find the length 2, right? The second length. It is the original length. The second length. That's what we're looking for. Is it clear?
yes,
What do? We know that the ratio of force to extension is constant. Do you remember?
yeah.
So what's F1? 4 Newton over the first extension, 0.02, is equal to what is 15 over the extension it will produce. Cross multiply, you have E2 will be equal to 15 times 0.02. 2 is 30, 0.3 or 3. 1, 2, 1, 2. That's 3 now. So 3,
0.3.
0.3, yes. Thank you. Yes, 0.3 over 4. Is that clear? So what would this give you? 0.75. 0.075. That's the E2. Is it clear? But the question, what does the question say? We should find the second length. So the second length is what? Original length plus 0.075. That will now be 4.075 meters. Is it clear? It says find the length of the string. So you have to add the original length plus the extension. Is it clear? Do you understand? A string that has original length of this is extended by 0.02 meters. This is the extension is given. I think they gave you the second length. It means you now get extension by subtracting first length from second length. So the extension is already given. So we write that. Then the load is 0.4 kg. See that load that's confusing you? It's kg. You know that weight of an object is what? Mass and acceleration due to gravity. So take that 0.4 times 10. Is it clear? Some question might give you 9.8. You just multiply by the value you are given. But this question did not give us anything because it assumes that you know the value of G. So G is 10. Is it correct? You multiply, you get 4. Then from here, it says that what will be the length? It's not the extension is asking us, it's the new length of the string when the applied force is now 15 newtons. So I will now take the ratio of the force and extension because it's constant. So F1 over E1 will be equal to F2 over E2. F1 is the first force over E1, the extension it produced was this. Bless you. Is equal to F2, which is the new force, over the extension that one produced. That's what we're looking for. So the extension it will produce is this meters. Then this extension will now be added to the new length. To the original length. Is it clear? Alright. Okay. Yes, you're correct. Should we go to the next thing? Alright. I'm gonna clean this. In the option they get that will be 4.08. Is it clear? Number 2, a piece of rubber. Because the concept of this is very simple. So they like to test other things, your understanding of other things, with questions like this. That one is for approximation now. A piece of rubber that long stretches 6 millimeters. So you see there's difference in this now unit. You have to convert. So a piece of rubber that the length is 10 centimeters. So the original length is 10 centimeters. Stretches 6 millimeters when a load. So that is stretches 6 millimeters. That's the extension. So L1, E1. Now what's the extension? 6 millimeters. You convert that. So from millimeter to centimeter, you do what? Divide by divide by 100. Exactly. Is it by 100? Look at it. 10 millimeter makes and 10 centimeter makes and 10 decimeter makes. So from this is 10 exactly. Divide by 10. So we have 0.6 centimeters. Alright. So this is the extension. It now says when the load of that is on. So the force is 100 Newton F1 is on from it. What is the strain? What's formula for strain? Extension of a length. You know, it's a very strange this thing. And the intention just added information that is not necessary. That will be 0.6 over 10. That will be 0.06. Is it clear? That's it. Right, the next one. The extension of a string when a 5 gram weight. Now listen. This yes, 0.06. Yes. There's no. Look at this. There's something here. Look at this. There's something I want to do. The extension of a spring. When do you notice they use string and spring now? So when you use spring, you don't need to put elastic. When you use string, you put elastic. The extension of a spring when 5 gram weight. Listen. You see, I will not convert it because they gave me 5 gram weight here and 5 gram weight, 20 gram weight. Right? So the extension of a string when this weight. So let's put it as F1 or weight 1. Is it clear? Yes, F1 will be 5 grams. But keep in mind that it's not like force here. For the force, you have to multiply by 10. But I don't want to do that because it's a waste of time. It's not necessary. The two are in grams. So in fact, we can call it weight 1. I hope it will not confuse you. Weight 1, good. So the extension is produced when this was on from it was this. So E1 is what? 0.56 centimeters. Let's see if we will convert. We don't need conversion. If you check your answer, what is the extension caused by this? That is, if you check your answer and your answer is in centimeter, you don't need to convert. Good. So the second weight is what? 20 grams. So what will be the extension that it will produce? So W1 over E1 because what? W2 over E2. So what's W1? 5 over E1, 0.56 is equal to W2. 20 over what is E2? That's what we're looking for, right? So multiply this by this guy. 25.6 times 2, 11.2 over 5. That is E2. Do you understand what I did? Just use your own calculator. E2 is equal to 2.24 centimeters. Is it clear? Alright. And for the sake of next time, see for speed, you know what I will do? Since I know it's just ratio they are taking, see, 5 grams is what ratio of this? Is 1/4. So this one will produce 4 times this. Do 4 times this, you get this. Right now, this one is just common on maths. It's just simple maths here. That's why I asked you to join maths class. Huh? Alright, should we do the last one now? Mama, I corrected her by her. Stay to it. Say, oh yeah, come and collect food. That's why she's your friend now. That's what they used to deceive themselves. Say, everybody is my friend. Now good to go. Let me ask you this question. The ray that causes gas molecules to glow is known as dash. The ray that causes gas molecules to glow. A. Gamma ray. B. Molecular ray. C. Cathode ray. D. Anode ray. Cathode ray. Cathode rays are electrons, streams of electrons. In fact, the next question now says cathode rays are dash high energy electromagnetic waves, B protons, C neutrons, D streams of electrons. Do you understand? Which of the following materials is a conductor? A. Sodium, B. Glass, C. Plastic, D. Wax. Good. The last one, a load of that F1 is 10, sorry, is 5 Newton. It's the same, they just multiply by 10. Wait, they use years. Is it clear now? Should I give you the one to solve now? Yeah. So do what is fair to the channel and share the video with your friend. God bless you.